So hi, my name is William Liu, and I am a senior at Princeton High School from New Jersey. And today I'm going to present my recent study. So my project is called Uncover the Risk Drivers for Wildfire Occurrence with Machine Learning Approach. So first, I want to talk about why did I choose this project. So understanding and predicting wildfire spread is really important because wildfire usually has devastating effects on the environment, on the human life, and even on the economics. So some examples of wildfire consequences include the massive atmospheric carbon emission, the degradation of water quality, and also a significant economic loss. And the challenges of forecasting wildfire events are usually associated with their intrinsic stochastic nature and the complex relationship between different categories of risk drivers, such as climate features, weather condition, vegetation coverage, and also land cover type. So typically, the next day's fire danger is predicted by indices like the Fire Weather Index, or FWI for short, which relies only on climate conditions and disregards other risk drivers like vegetation coverage and human behavior activities. In this research, we applied data-driven machine learning methods to predict the fire danger for the region from British Columbia in Canada all the way to Oregon in the United States. So here are some data resources we used in our study. So the first, we have the active fire data from the MODIS dataset, collection 6.1, between 2015 and 2020, provided by the NASA firms. So for the time period of 2015 to 2020 in the region we selected, there are 147,222 daily fire event spatial temporal data. And the selected study area is with latitude from 42 to 55 and longitude from -117 to -130. And this covers the region from British Columbia in Canada to Oregon in the US. And this region also features dense forests, mountains, and increasingly prolonged summer droughts. The important features for the predicting wildfires include using the weather data, vegetation coverage, and land cover type represented by normalized difference vegetation index, or the NDVI for short. We downloaded daily weather data and vegetation coverage data from reanalysis product of ERA5 land dataset from the climate store of ECMWF. For land cover data, we downloaded the graded daily normalized difference vegetation index from the NOAA climate data record of visible infrared imaging radiometer suite surface reflectance. And here are some input features for predicting wildfire events. So first, we have the 10-meter wind speed, which aggregates 10-meter vertical speed and 10-meter horizontal speed into a directional speed, just like vectors. We also have 2 meters temperature and 2 meters dew point temperature data. And from these two measurements, we can calculate the relative humidity. Next, we have daily average precipitation and the daily average temperature for the 30 days prior to the data. We also have vegetation coverage, such as leaf area index, or LAI for short, for both low vegetations, including shrubs and grasses, and also high vegetations, which includes forests. And lastly, we calculated the distance to the closest developed land using the normalized difference vegetation index. So next, we're going to introduce the methodology for this study. So we treat the wildfire probability forecast problems as a binary classification problem, or in other words, we treat an event as either fire or without fire. The input features were taken from the reanalysis product, or the ERA5 land dataset, and the relative humidity was calculated from the 2-meter dew point temperature and the 2-meter temperature as discussed before. And we further calculate the average precipitation and the temperature in the previous 30 days as the prediction variables. The reason why we choose these two variables is because precipitation and temperature both have long-term effects on vegetation health and moisture level, which directly affects the occurrence of wildfire. And considering the potential effect of human activity on fire occurrence, we also calculate the closest distance of fire location to develop land area that were identified by NDVI index. And finally, this results in 10 input features, 6 directly from the ERA5 land data, and 4 calculated from the ERA climate data and also the NDVI land cover data. For our models, we used the random forest and the extreme gradient boosting models, or the XGBoost. These two models are both man tree-based supervised algorithms involving training and ensemble of decision trees. And we use these two models in our study to classify fire events. And before that, we first applied the decision tree to produce a set of rules that are easily interpretable and a flow diagram to demonstrate the rules. So here is a sample decision tree. So as we can see from this decision tree, we have our land use data as the most classifier. So for example, if we have a land a distance to the closest developed land to be less than or equal to 0.028, then the event is identified as a non-fire event, or a class 0. And if that identifies as false, then we go to the next variable, which is still land use data. Land distance data. But now we're checking if the distance is less than or equal to 15.998. And if this is true, the event is evaluated as a fire event. And if this is false, we go on to the next variable, which is the average precipitation, and so on. And here are some graphs, distribution graphs we used to identify which input features we're using. So for example, in the first graph, we have fire data graphed out by the red curve, and the non-fire data graphed out by the blue curve. And as we can see, fire data are centered more around 0.8 with a lower relative humidity, while non-fire data are centered closer to a relative humidity of 1, which is associated with higher humidity. So in this case, we can identify which variables we're going to use in our study that are going to contribute to the classification. And here are some metrics we used. The accuracy, which measures the overall percentage of correctly classified fire and no fire events. But for an imbalanced dataset where we have much more non-fire events than fire events, the accuracy is not a good metric. So we introduced the F1 score, which is a harmonic mean of the precision and the recall of the confusion matrix of a classification model, and it provides a better metric. We also use the ROC curve to compare the false positive rate with the true positive rate for model performance. And the area under the ROC curve is used as a metric for assessing the model's effectiveness in distinguishing between a correctly predicted fire event versus a wrongly predicted fire event, with a area closer to 1 representing the model is more effective. And here are some heat maps we use to identify the distance to the closest developed land as our variable. So, here are some results we got from our models. We used 2 different trials. The first one is random sampling, where we random sample 60% of the data set to be the training set, 20% to be the validation set, and 20% to be the testing set. And we got an accuracy of 87% for random forest and 88.7% for XGBoost. And for the second trial, we used the data from 2015 to 2018 as the training set, and the data from 2019 as the testing set, and 2020 for the validate set. And we got a even higher accuracy of 90.3 for random forest and 90.6% for XGBoost. And in general, these results are all demonstrating that the models are effective. And after presenting the results from the models, we also analyze the importance of the input features. So we use the Shapley values, which computes the marginal contribution of each feature, or in other words, how much each feature contributes to the classification of the fire event, where a positive Shap value means a contribution to causing the fire event, while a negative Shap value means a contribution to reducing the risk of fire events. And here is a summary plot for our Shap values. And we can notice that most of the active fires are associated with a lower distance to develop land, and the higher temperature and lower precipitation in the previous months contribute to increased fire dangers, while on the other hand, the higher surface pressure and higher humidity contributes to lower the fire risk. And lastly, I want to share some conclusions from our paper. So this paper contributes to existing data-driven research by applying NASA active fire data and the ERA5 land dataset to uncover some major risk drivers behind the wildfires in the region of British Columbia and Oregon border. And for the two versions of tree-based algorithms we trained, which are random forest and XGBoost, the XGBoost model is more accurate and effective. But in general, both models are great. And the relationship emerging from the machine learning model reveals the importance of fuel-related variables as distance to develop land, NDVI, and relative humidity. And lastly, most of the fire events in the region we studied occurred closer to the developed land, indicating the importance of human behavior and human activities in the wildfire prediction. And thank you for listening to my research experience.